Back. So here we're going to start into section 4.4. Shout out everybody that's out here. Shout out. Hope you're doing well at home, Popio.
Shout out, Pope.
Let's see if he's actually going to watch the video.
Yeah.
They have zero confidence in you, Nathan. Don't kid yourself. All right, so let's talk about where we're headed in chapter 4. So we've already done the 4.1 to 4.3 quiz, right? I'm leaving time in between now and the test for two reasons. One, for you, if you'd like to retake that quiz, I am going to open that up for a retake. Let me grade the originals before you just say you want to take a retake. I'm leaving some time in between now and then for a retake, and so that you, like, if you did not do so well on it, time for you to like look back and say, okay, what did I actually do on this? Where did I go wrong? Where did I go right? Because I'm guessing for a lot of you, there were just little mistakes in there which threw off the rest of the problem. And if you make those little mistakes, it can kind of snowball a little bit. So here's where we're at now. Okay, so we're going to do section 4.4 on Monday and Tuesday. Okay. Now, I believe. Oh, did I save that halfway through? Oh, shoot. Oh, no, I did. Okay, good. I have the correct problems up here. Because what I did last year, I kind of like ditched what I did last year. I don't love the problems in like the actual section of the book, so I took a lot of the homework problems and like made them classwork problems. So we're going to do that today and tomorrow. Hopefully get done with the notes about halfway through class tomorrow. And then on Wednesday through Friday, we are going to review 4.1 to 4.4. Okay, because next Monday and Tuesday, and understand if this is a snow day, if there's a snow day in here, everything will get pushed back a day. Monday and Tuesday, we will have our 4.1 to 4.4 test. Oh, you'll be fine.
This is a short chapter.
Now, this chapter is broken up into two pieces. The 4.1 to 4.4 and then 4.5 to 4.8. We will not have a full chapter 4 test. Okay? So this is broken up into two parts. 4.1 to 4.4 and then 4.5 to 4.8. I'll tell you that 4.1 to 4.4, there's a little bit of graphing like we did in section 4.3, like you saw on the back page of the quiz. The 4.5 to 4.8 is a lot of graphing. Yeah, we will use everything that we've learned from sections 4.1 to 4.4 with some additional stuff 4.5 to 4.8. We'll do a quiz and a test just like we had within the first part of this chapter, and that will probably take us through the end of the third 9 weeks. Okay, I would love to try to hold off and take that test and have that last test, that 4.5 to 4.8 test, be the last thing that we do in the third 9 weeks. I don't want to get too far into chapter 5 before the start of the fourth 9 weeks, because there needs to be some grades in the fourth 9 weeks. So we might end up like getting into chapter 5, but I want to hold off on that chapter 5, any assessment in chapter 5 until we get into the fourth 9 weeks. And isn't it crazy? We're talking about the fourth 9 weeks of your senior year. Well, most of your senior years.
I'm an honorary senior.
No, you're not. All right. Okay, so let's talk about section 4.4. Indeterminate forms and this thing called Lhopitals Rule. Now,
What is first?
it's this guy. His name is Lhopital. Yeah. Lhopital. That's how you pronounce his name. Lhopital. Now, if you have friends in AP Calc, they actually don't learn Lhopitals until way later. And it's just the way the curriculum lines up. Honestly, we could have learned Lhopitals Rule right after we learned derivatives. Okay? I'm not exactly sure why it's right here, right now. It's kind of like we've done all of this stuff about derivatives and how they affect their graphs and whatnot. And now we're going to like jump backward a little bit and talk about limits. Okay? Basically, what we're going to be doing is we're combining our knowledge of limits and our knowledge of derivatives, basically. That's what Lhopitals Rule actually does. Now, to understand how to work with Lhopitals Rule, you need to know what an indeterminate form is. Okay, and there's several indeterminate forms. Like, for example, consider this function. ln of x over x minus 1. Okay, ln of x over x minus 1. What if I wanted to take the limit as x approaches 1? Could I do it? Well, I guess I should say it this way. Can I do it by direct substitution? No, obviously not, because if I put it into the denominator, I get a 0 in the denominator, right? And we would say, nope, can't do it by direct substitution. But, maybe there's some weird way that we could manipulate this, like we did in chapter 2. We factored and we reduced down, and then we were able to directly substitute later on. There is one that we could look at the graph and see what's happening at 1, if we really wanted to. But again, we're not really concerned about what's happening at 1. We're concerned about what's happening near 1, right? Now, this is actually what's called an indeterminate form. Okay, this is actually what's called an indeterminate form. Before we would just say, oh, we can't do it, right? Because divide by 0. But this is actually, but the formal way to talk about that is what's called an indeterminate form. In computing the limit, we can't apply any of the laws of limits because the limit of the denominator is 0. In fact, although the limit exists, its value is not obvious because both numerator and denominator go to 0. And that's what's unique about this. That's what makes this an indeterminate form. Not the fact that the denominator just equals 0. The fact that both the numerator and the denominator go to 0. For example, take a look at the numerator. What's happening at ln of 0? What is compute ln of 0? Think about this. What is ln? When does this equal 0? I guess that's what I'm saying here. Right. Well, to solve that, maybe it would be better just to put this in log base e and just solve for x. E to the 0 equals x. What is e to the 0? Oh, sorry. Whoops. What is e to the 0? 1, obviously, right? So 1 is x. So that means, I'm sorry. I had this the wrong way around. I'm plugging in 1. I want it to come out to be 0. Oops. Because if we evaluate 1, that's what I'm looking at here. Sorry. If I'm evaluating 1, because that's what we do when we do direct substitution, right? We plug in the value in for x. Same thing here. Log base e of 1 is something, right? So e to the something is 1. And then we could say, what is the value of e to that thing? What is that question mark? E to the what gets us 1? Well, anything to the 0 power is 1. So if I directly substitute, I'm going to get 0 over 0. And that is why it's an indeterminate form. Not the fact that the denominator goes to 0, but the fact that both numerator and denominator equal 0. And there's actually a lot of what's called indeterminate forms. We will talk about them probably tomorrow. Okay, there's a bunch of indeterminate forms. You can have 0 over 0, infinity to infinity, infinity over infinity, infinity times infinity, 0 times infinity. There's a lot of different indeterminate forms. This is one of them, 0 over 0. Okay, and that's, there's part of the homework assignment where it asks you, okay, what type of indeterminate form is it? Well, this is a 0 over 0 form. Now, why is it important to know what indeterminate forms are? Well, because if you have an indeterminate form, you can apply this thing called Lhopitals Rule. Okay. Suppose that f and g are differentiable. Now, be careful here. What we're looking at here is always going to be a rational function. Okay? This is always going to be a rational function. Or something that you could turn into a rational function, something that you could turn into a quotient. Suppose f and g are differentiable, where f is the numerator and g is the denominator here. Okay? And that's down here. Suppose that f and g are differentiable, where f is the numerator and g is the denominator. And as long as g prime of x is not equal to 0, right? As long as we don't have a 0 in the denominator. On an open interval I that contains a. So basically saying, as long as we can actually compute the limit, that the limit actually is computable on both numerator and denominator. Suppose that, okay, the limit of the top is 0 and the limit of the bottom is 0. Basically, it's an indeterminate form of the 0 over 0, or an indeterminate form of infinity over infinity. That's another indeterminate form. So the limit as x approaches a is either positive or negative infinity of f of x, and the same thing as g of x. Okay, if I can plug it into both the numerator and denominator, and it's going to go to infinity or negative infinity in both the numerator and denominator, we have what's called an indeterminate form of the infinity over infinity. So as long as you have an indeterminate form, and that's very important to make sure that you have, because if you don't have that, Lhopitals rule does not exist. Okay? As long as you have an indeterminate form, what you can say is that it's the limit of the function f of x over g of x is actually equivalent to the limit as x approaches a of f prime of x over g prime of x, which is really quite interesting. The limit as x approaches a number of this rational function, f of x over g of x, you can actually set equivalent to the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator. Now be careful here. I am not doing any sort of quotient rule. That's not what I'm talking about here. That's the tendency. That's the main mistake I see a lot of people do. You try to differentiate and you see a fraction and you're like, oh, I got to use quotient rule. No. We are taking the derivative of the numerator and dividing it by the derivative of the denominator. Okay? So that's basically Lhopitals rule in a nutshell. If it meets the criteria of being an indeterminate form, you can take the derivative of the numerator and the derivative of the denominator separately, not as a quotient, but separately, and evaluate the limit, keeping the same value here. Like, I didn't change that. The limit as x approaches a. You can take the derivative of the numerator, derivative of the denominator, and find the limit of that, and that will be the final limit as well. Okay, so a couple notes here. Lhopitals rule says the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. It is extremely important to verify those conditions regarding the limits of f and g before using Lhopitals rule. Because I could see myself asking you, like, does Lhopitals rule apply on this? Not necessarily making you perform it, but asking you, does Lhopitals rule apply? And then you have to say yes or no based on, is it an indeterminate form or not? Is it a 0 over 0? Is it an infinity over infinity? What is it? What type of indeterminate form is it? Second thing, Lhopitals rule is also valid for one-sided limits. You can actually compute a one-sided limit with this. All of those rules apply still. If I put a little negative or positive on A for any of these, you could still apply Lhopitals rule. And I'm not going to talk about that special case. Let's take a look at this. Hey, this is the example that we were considering at the very beginning, isn't it? And we said, oh, we can't do it. But if we apply Lhopitals rule, it actually becomes quite easy. And for example here, if I want the limit as x approaches 1 of ln of x over x minus 1. Now, I'm going to show you, if I had not gone through the process I had in the very first slide, this is what I would have to write out. Okay? I would have to say the limit as x approaches 1 of ln of x. Okay, we saw that that was going to be 0, right? Was 0. If I plug in ln of 1, like, and I could just go to my calculator and do it too, ln of 1 is 0. Because log base e to the what is 0? X would be 0. If I plug in 1, I get 0. Same thing on the bottom here. The limit as x approaches 1 of x minus 1 is also 0. What am I doing here? I am setting up the premise, I'm setting up the hypothesis of Lhopitals rule. I'm saying, so this is an indeterminate form. Indeterminate. Okay, I just want to make sure I spelled that right. Indeterminate form of 0 over 0. Math teacher, not can't spell. Indeterminate form 0 over 0. So you have to set up the premise. You have to show that it meets the criteria. Okay, so now that it meets the criteria, we know that this is going to be the limit as x approaches 1 of the derivative of the numerator. Again, don't use quotient rule here. I'm finding the derivatives separately. What's the derivative of ln of x? Anybody remember? 1 over x. Divided by, well, what's the derivative of x minus 1? 1, right? What's the derivative of x? 1. What's the derivative of minus 1? Nothing, right? So this actually just ends up being 1. Or in other words, the limit as x goes to 1 of 1 over x. Okay, now can I directly substitute? Yes. See how easy that was using Lhopitals Rule? Something that would have been very, very difficult to compute. Something that would have, we would have been stumped in chapter 2 if I would have given you that limit. But as long as it fits the criteria of having a 0 over 0 or infinity over infinity, I can say, yeah, it's in that indeterminate form. So now I can say, take the derivative of the numerator, then the derivative of the denominator. Boom, done. Okay. Let's take a look at this next one. Okay, let's see if this is another indeterminate form. Because it's got to be 0 over 0, infinity over infinity. Okay, so I'm looking for the limit as x approaches infinity of e to the x over x squared. Okay, that means I'm going to check. Now, I guess I should start this. If I'm using direct substitution, could I find it? No, because watch what's going to happen. The limit as x goes to infinity of e to the x, well, if I plug in infinity to e to the x, isn't it going to keep getting bigger and bigger and bigger and bigger? Right? E to the, bigger power is just a bigger number, right? Is infinity. Same thing here. If I go to infinity of x squared, same thing. Just more positive infinity. So what I'm showing here is that this meets the criteria of being able to use Lhopitals Rule. Okay, we can say that this is an indeterminate form, infinity over infinity. And now I can use Lhopitals Rule. The limit as x goes to infinity of, okay, what's the derivative of e to the x? E to the x. What's the derivative of x squared? 2x. Okay. Ruh-roh. Because if I try to plug in again, I'm going to go to infinity in the top and then infinity again in the bottom, right? The limit as x goes to infinity of e to the x is still infinity. That didn't change from my first time. The limit as x goes to infinity of 2x is infinity again, right? Oh, this is another indeterminate form. So it's kind of like a Lhopitals rule inside of another Lhopitals rule. Yeah. L'Hopital inception. So this is another indeterminate form, infinity over infinity. So I can actually find the derivative again, which is really quite easy, right? Especially with the functions that we have. So this is equivalent to the limit as x goes to infinity of another e to the x over now just 2. Right? Okay, well, if I directly substitute, this is infinity on the top divided by 2, but infinity divided by 2 is still just infinity. Okay? Because you might be tempted to, if it was like infinity over infinity, you might be tempted to say 1, right? Because it's the same thing over itself. You might be tempted to say 1, but Lhopitals Rule says no. It's not 1, it's actually infinity. It's going to be infinite. Okay. Can we do it again? Yes.
And you can do this with, like, if it's negative infinity over infinity.
Yeah, the sign doesn't matter for that.
Okay.
Yeah, because it's still going to be an indeterminate form. That's why there was a plus or minus in between these.
I was just wondering if there was like any
if there was like one negative, one
could be at the
positive.
top or something like that.
Yeah, it doesn't matter. It doesn't matter. If you've got any type of infinity over any type of infinity, you can use Lhopitals Rule. Now, I think you guys are going to see that the more difficult numerators and denominators I give you, the more difficult the problem, okay? A lot of the homework is very similar to these three types of questions where I just keep asking you, can you use it? So use it. If you can't use Lhopitals Rule, then you just stop, okay? You can't use it. All right, so let's calculate this limit. We've got the limit as x approaches infinity of ln of x over the square root of x. Now, if we plug in, let's go to the top. Let's find the limit of the top, the limit as x approaches infinity of ln of x. Now, think about ln of x. If I go y ln of x, zoom 6. It's going to keep creeping upward, right? So no matter what, if I plug in infinity, it's just going to keep. Is there ever any horizontal asymptote to any logarithmic? No. So you might be tempted to say like, oh, it levels off somewhere. No. That's not true. On the right side of this, and that's really what we're saying here with the graph, right? At limit as x approaches infinity. As I keep going right, it's just going to keep getting bigger and bigger and bigger. But it's creeping up. It's going there slowly. But it's still going to go up eventually. Look at the bottom. The limit as x goes to infinity of the square root of x. Same type of thing here. Think about plugging it in. You square root any number, and you just keep getting bigger and bigger and bigger. The square root's going to be getting bigger and bigger and bigger as well, right? There's never going to be any boundary to that. So that's going to go to infinity as well. Same type of thing there. You could have looked at the calculator for that as well. Let me do that. Square root of x. Same type of thing. It's going to keep creeping upward. So like you might be tempted to say, oh, this maybe are creeping upward at the same rate, so maybe it's just 1. Be careful with that. Okay, be careful with that. That's not true. What we have here is an indeterminate. Indeterminate of the form infinity over infinity. Okay. So let's apply Lhopitals Rule again. Okay, that means we have the limit as x approaches infinity of, okay, we talked about this already. Ln of x is 1 over x. And then the bottom becomes the square root of x, taking the derivative of the square root of x. So now remember that is like saying, whoa, where'd you go there? That is like saying ln of x over x to the 1/2 power, right? It's been a minute since we've done like a square root. That's pretty laggy over there. A square root derivative, isn't it? Okay, so let's think about this. D over dx of the square root x to the 1/2 power would be 1/2 x to the negative 1/2, right? 1/2 x to the 1/2 minus 1 is negative 1/2. So that's like saying 1 over 2 radical x, right? That's what we have here. That's the derivative of x to the 1/2 power, which is basically the square root of x. So 1 over 2 radical x. Now let's reduce that down a little bit. I've got fractions within fractions, so let's reduce that a little bit. Forgive me for not writing the limit again. 1 over x. I'm going to multiply by the reciprocal, 2 radical x over x. Oh, over 1, excuse me, over 1. Okay, so this is 2 radical x over x. Now, thinking about it this way, isn't this x to the 1/2 power over x to the first? What would I do with those exponents? Subtract, right? So this ends up being 2x to the negative 1/2 power, right? So in other words, limit as x approaches infinity of 1 over 2 square root of x. Oh, no, sorry. The 2's on top. Yeah, just the radical x moves down. Now, okay, I put infinity. If I put infinity in there, I'm going to square root infinity. It's just going to keep getting bigger and bigger and bigger, right? Now remember, what happens if I keep making the denominator bigger and bigger and bigger and bigger? What's it going to go to? 0. It's going to go to 0. That's my answer. See, I think you can see the more complicated I make the original numerator and denominator, the more complicated things are going to get. You just have to keep making sure that Lhopitals rule applies. The original premise, the original hypotheses apply. Got to make sure of that in the indeterminate form. Okay. Oh, we got about 10 more minutes. Let's do a couple more problems. We'll start the day tomorrow with that example 4, with this tangent one. Okay, let's do this one. This one might seem like it would look a little bit more difficult, but the thing is, you're going to say, oh yeah, polynomial over a polynomial, that's good. You want to know why? Because the derivatives are super easy with a polynomial. Super easy with polynomial. Here's the deal. What you have to do is say, okay, make sure the limit as x approaches 2 of x to the third minus 7x squared plus 10x. Let's see what that equals. Well, let's plug it in. We got 2 to the third minus 7 times 2 squared plus 10 times 2. Okay, that's equaling 0. The limit as x approaches 2 of x squared plus x minus 6. Well, that's 4 plus 2, 6 minus 6 equals 0. So we can use Lhopitals rule. This is an indeterminate. I'm okay if you abbreviate. Indeterminate form 0 over 0. Okay, so let's do the derivatives. X approaches 2 of 3x squared minus 14x plus 10 over 2x plus 1. Okay, now let's plug in 2. Make sure I did that right. 3x squared minus 14x plus 10. Okay, good. I did that really quick. 3 times 2 squared minus 14 times 2 plus 10. That'll give us negative 6. So I know that this, like whatever I get on the bottom, this is not going to be an indeterminate form, right? Even if I get a 0 on the bottom, then it would just be undefined. That means the limit does not exist. Okay, the limit exists here. It's just an indeterminate form. And then we do, 5. Okay. So negative 6/5. That's the limit. Really easy using Lhopitals rule, right? If I had tried to factor down even, like maybe I could have gone at this problem in the way of like trying to factor it down to reduce it. But did I even need to? No, because Lhopitals rule applied. And that made it a super easy problem because we know how to do a derivative. Yeah? See, we couldn't do this back in the limit chapter because we had not learned derivatives yet. Like we had to wait until we learned to do a derivative until we apply Lhopitals rule. Okay. All right. I'm going to stop there. That was a lot for today. Let's be done for today.
This just feels so